Welcome to lecture 8 of the spectral module section. This will be the last lecture in this module, both for the Toolkit course as well as for the HDX series. For the Toolkit, starting Thursday, we will start the next module, which will be multiplicative weight update methods. For those who are continuing on the HDX series, we will send you an email shortly. We'll most likely do a joint viewing of Alex Lubotsky's Minerva lectures. So we'll view it on YouTube. It's a bunch of lectures on YouTube. We'll view it jointly. And this will be moderated by, I think, Arghya Mandal. Not sure. You'll get an email about that. But let's get back to spectral graph theory. So last lecture we had seen, in the previous lecture, we had seen a couple of examples of, we had defined the notion of expansion, expander graphs, both spectral expanders and vertex expanders. And we showed that these expanders, we saw last lecture, we saw some amazing applications of these expander graphs, particularly the randomization. They were helpful to reduce the number of random coins required in algorithm. And these constructions required that we have expanders, and not just any expanders, we needed fully explicit constructions of expanders. Expanders exist. A random graph is going to be an expander, but we actually needed a one. And for this purpose, we had given various constructions listed out some constructions, the Margulis construction, the construction of Ramanujan graphs by Lubotsky, Phillips, Sarnak. But we didn't prove that these were expander graphs. We just stated without proof that this is we gave the adjacency matrix representation or the adjacency list representation and said these were good expander graphs. What we'll see today is an alternate construction of expander graphs, and we'll actually see the construction completely, and we'll also see a proof of the fact that it's an expander graph. Okay, that's going to be this one. So today, what we'll do, we will see the zigzag construction of expander graphs. And this will be a very computer science-ish construction, unlike the previous constructions, which were just based on some number theory facts. Based on that, we proved it. We will actually take an expander graph, which we have a small sized expander graph, say a graph on 10 vertices, 20 vertices, and then we will build larger and larger expander graphs. We'll use this as a sort of a base step and induct on this to build larger and larger. So we will build expander graphs. From scratch. Assuming a fixed constant size expander graph. So suppose we have an expander graph on, say, 10 vertices or 20 vertices. We'll take this as a starting point and see how we can construct expander graphs on more and more vertices. We won't be able to construct it for every n, but infinitely frequently large enough n, we'll construct an expander graph. The goal will be, we have a fixed, what we want is we're going to fix a degree d and some eigenvalue lambda. As long as both of these are constant, we are fine with it. I don't care for the right Ramanujan graph, like d being lambda being 2 square root d minus 1 by d. That's not what we care for. We just get two fixed constants, d and lambda. D some number larger than 3 and lambda to be some number less than 1. And we'll construct a family of expander graphs for infinitely many n. such that you will construct for each of these n in the family will construct an ND lambda expander graph. Okay. So a few things that so we want to take a one, and the construction will actually be, we'll first construct, we'll give the basic steps for this construction. We want the construction to be a fully explicit construction. That is, if I give you a particular vertex, you must be able to tell what are its D neighbors in time, polylog n time, where n is the size of the graph. It could be explicit if you give it to me in poly time, which is in the size of this one, but we'll actually ask for polylog n. Okay. So what do we need now? So we are given a particular graph. Say we are given. So let's ask for graph operations. What I want by this is, suppose I have a particular graph. What all can I do with it? What are other related graphs that I can construct, whose eigenvalues I sort of do know? So suppose G is a n, we'll use this notation. So G is a ND lambda spectral expander. I want to do a bunch of operations on this graph to get larger graphs. Graphs on, typically I would like to keep B and lambda to be the same and n to be larger and larger. I have it for one fixed n. Think of n right now as some 10 or 100. What can I do? For this one, so let's basically, we need a couple of things. We need to understand, because we're going to build the graph, we need to understand how the graph is represented. So the most natural representation is the sort of the graph representation. Is one representation which you'll use quite often is the adjacency list representation. What do I mean by this? I'm going to give a function gamma from n cross d to n. So u comma I will be mapped to b, where b is the ith neighbor of u. So I want, so giving a graph explicitly is going to be, I need to give up an algorithm that outputs this stick. You give it n, you give it something between 1 to n, and between 1 to d, it outputs 1 to n. So that's the adjacency list representation. More particularly, say if the graph is like this, it has d guys. So this is 1, 2, 3, 4, 5, and this is u. So this is this first neighbor, second neighbor, the third neighbor, the fourth neighbor, and the fifth neighbor. Now notice that this is the link. So let me write this, draw this a bit. We have this graph G. And there's a vertex U. And it has 5 edges going out of it. Let's call it H1, H2, H3, H4, H5. And these are the neighbors. U1. Let's call it consistent with what I said. V1, V2, V3, V4, and V5. So in particular, gamma U of 1 is, more generally, gamma U of I is Vi.
We are thinking this sort of a directed thing, but labels are on the edges.
So labels are on the edges. That's what I want to say. So this is use first neighbor, second neighbor, third neighbor, fourth neighbor, fifth neighbor. Now, from V1, this need, so what Mrinal is asking, is this label on the edge 1, or from V1 is also going to have 5 neighbors. So V1 say it's going to have, let's look at it from V1's point of view. One of which is going to be this particular guy itself. So this edge is 1. Now the question is, it also has a labeling. what is its labeling? You could have a consistent labeling that if you take the first edge out of U, you go to V1, and then the V1's first edge is also U1, but don't have to name it. We'll just put an arbitrary labeling. So V1 has its own labeling. Say, call it 1, 2, 3, 4, 5. So the first edge out of U leads to V1, but the fifth edge of V1 is the same edge going to this one. So it will be that gamma of V1, comma 5 in this is U. So every edge gets two labels, which is what is the edge corresponding to this particular vertice's viewpoint. The two vertices could have different viewpoints. You could have a consistent labeling such that the two vertices are the same. This one that need not be true. So, but this is now this labeling is trivial to get. Given a graph, I can just go and label everything this way, and you get it. To get a consistent labeling is not easy. Not clear how to do it. The way to do it will be you'll have to peel out matching after matching. You take a matching in the graph and label all the edges in the matching with a particular number. Then take another matching, keep peeling it off, and that's one way of doing consistent labeling. But we are not going to assume consistent labeling. So this is it. So we'll actually come up with one more representation called the rotation map representation, which makes this explicit. The rotation map representation, this is in general, there's always a gamma G, which sometimes I'll drop. There's an underlying graph, and that's the neighborhood of that gamma G. The rotation map is rot G. It's N cross D to N cross D. So it not only tells you who is my ith neighbor, it tells me what am I to the other vertex. So for instance, it's going to map U, comma I to V, comma J if ith neighbor of U is V and the jth neighbor of V is U. So it's telling you exactly, in Jay Kumar's word, is sort of this number tells you hum aapke hai kaun, who are you to me. So it is sort of you are my ith neighbor, what am I to you? You are my jth neighbor. I am your jth neighbor. It's sort of giving you this information. Notice rot G and D is a permutation. It's a permutation. Once, because if you go from U to I to V to J will take you back to, it's not just a permutation, it's an involution. If you apply it twice on the same thing, you'll get back the same thing. The rotation map. Is an involution. That is dot G of U of I equals V of J implies dot G of V of J equals U of. So we'll actually ask for the more this one. Can we actually come up with a rotation map for this one? So when I want to ask fully explicit, what we'll ask is, can I give you an algorithm that given me N, D will output these both, and it will run in poly time in its input, which is poly log n in the size of the graph. That's what we care for. Okay. The most simple of the graph operations is, of course, going to be graph powering. So in general, let's look at G2. This is just going to be the graph in which or more generally G T graph in which there exists an edge GT for every path of length T, that is T edges in the path. In G. For every path, and we'll put it with so much multiplicity. We'll actually, it's an adjacency matrix typically has been a 0, 1 thing, but we look at it weighted. If there are two paths for between U and V of length 2, we will put it with a number 2 over there. Right? Say it's with multiplicity. It's exact. So more precisely, what would so if you are given, if you give to me rot G for this one, from that, how will I get rot G square? So if I give you U and I1, I2, on input U and I1 and I2. One second, let's maybe a little more precise what I'm doing. So we are going to be given rot G, which is N cross D to N cross D. And from this, assuming this, I want to construct rot G square, which is going to be from N cross now D cross D, because there are two. This is going to be a path. This is going to be rot G square will be a graph of degree D square. And more precisely on input U comma I1, I2. We first compute rot G of U of I1, which say is VI2, VJ, let's call it VJ2, VJ1, VJ1. Then you compute rot G of, you take the next step, V and I2, and suppose that is WJ2. Then what will you be outputting? So the neighbor of this, the I1, I2 neighbor of it is W, but you have to also tell me how to get to it. So it will be J2 comma J1. You take the J2 step and then the J1 step. That's what.
The row square in the rod G square.
Where?
D plus D whole square.
Oh, yeah. Sorry. I notice the adjacency matrix is just going to be the square of the adjacency matrix. If you have AG of AG square, will exactly be AG square. Now, let's just do this observation. So suppose G is a ND lambda expander. What will G square be? How many vertices are there in it? N D square.
So maximum lambda is the maximum of lambda 1, lambda 2 and mod of lambda, right?
Yeah. So more precisely, suppose AGF was lambda F. We had a particular eigenvector eigenvalue pair for AG. For AG square, this is, we have AG the whole square. What is AG square F then? Lambda square F. So the set of eigenvectors will be the same set of eigenvectors, and all the eigenvalues will just be squares of the previous set of eigenvalues. So what will lambda be? Lambda will be lambda square. So let's look at this. We are looking at this process. We have a particular graph. We're going to try to construct larger graphs out of it. So this process, each time we are going to do a process, it's going to affect the number of vertices. It's going to affect the degree of the graph. It's going to affect the spectral gap. There are these three operations. Let's find out graph powering. What does it do to these three operations? We already, that lemma out there says it, but I'm just writing it more. It's number of vertices.
Why the adjacent symmetries of these square will be square?
Huh?
Why the adjacent symmetries of these square will be linear?
Let's look at it. But okay, good question. Let's see that. What is AG square of UW? This is exactly sum over all V
And the two lengths pass.
AG UV AG VW.
Okay.
This is not AG square. This is just AG whole squares. That's exactly what it is. And that's exactly, you're counting, starting from U and W, you're counting all parts of length 2. And that's exactly what that's why I'm I'm putting the number of parts. And this will be true for any AG, any powering, this will be exactly the same thing. It's just matrix multiplication behaves very nicely with powering. So eigenvalues of AG square or squares of eigenvalues of each. So let's look at these three. For squaring, of course, this is going to be very easy. Degree and the second and lambda. And they call the lambda. So this is unchanged. And that's not a good thing for us. That's actually a bad thing. We want to build larger and larger graphs. This is actually increasing. That's also a bad thing. Actually, this if I call among bad things, this is the really bad thing. The degree you don't want it to increase. I want to keep the same degree graphs. This is going. This one, at the very least, it's not worsening, but it is remaining the same. But this is decreasing, and that's a great thing. So squaring is not what we ever wanted to do. I didn't want to actually get a better spectral gap. I just wanted to get a graph and larger number of vertices. Squaring did not achieve what we wanted to do. There's another operation which will actually produce this one, which is called graph tensoring. So suppose G was a ND lambda expander and H was a small n small d mu expander. We'll now define a graph called G tensor H. What is G tensor H going to be? Its vertices are going to be pairs of vertices. So it's to make up for the fact that you're not building larger graphs. So the vertices of G tensor H are exactly going to be the vertices of G cross product vertices of H. Okay. And what are the edges of G tensor H? The edges of G tensor H is, I'm going to ask, when is U1 V1 connected to U2 V2? This connection is G tensor H. We'll say this is true if and only if U1 is connected on G to U2 and V1 is connected via H to V2. So it's basically you just take the two graphs, you're taking a step in each of the graphs. So more precisely, ROT G tensor H of U1 V1 I1 J1 will be U2 V2 I2 J2 if ROT G of U1 I1 equals U2 I2 and ROT H of V1 J2 J1 equals V2 J2. Okay. This is certainly building a larger graph. You could tensor the same graph with itself, building a larger graph. Let's try to understand how the adjacency matrix looks like. And then based on it, let's try to understand what are the eigenvectors and eigenvalues of this graph. So how will the adjacency matrix of G tensor H look like? It's a tensor product, or if you want to, this one, it's going to be on n vertices. And you can think of it being broken up into chunks of, these are each one of them is an n cross n vertex, is itself an n cross n matrix. In which you're going to put the adjacency matrix of H. And then, so think of putting for every square such matrix of n cross n, you put the adjacency matrix of H. And you scale it by, and then have the adjacency matrix of G globally, and then scale each one by whatever the adjacency matrix of G says for that value. If G says 1 for the ijth entry, go to the ijth, the whole thing, and just replace it with that times 1. If it says 0, replace it the whole thing with that times 0. So more precisely, I'm just saying this one, that is mg tensor H, what this exactly what we had before, U1 V1 U2 V2 is exactly mg U1 U2 times mh, sorry, these are not all m, these are all a's, ah V1 V2. It's just the product. One. I have thought of it as a big n by n matrix whose small entries are all small n by n. Of course, you could think of it the other way. It depends which way you want to write things down. Now let's just say was AG has eigenvector values fi comma lambda I going from 1 to n, and AH gi mu I gj mu j going from 1 to n. Then I want to find out what are the eigenvector. Basically masking AG tensor H. What will its be eigenvector?
So we can do the math. I've seen this sort of thing before, but and so in the earlier the powering thing, it felt like so I want to just to intuit this. I want to instead of think of eigenvalue, I want to think of conductance, which feels like a more because these are sort of the same things.
Modulo the quadratic factor, they are not exactly.
There's a point, but if something grows, this should also grow. If this goes down, and you're doing powering, it's sort of like you're sort of amplifying the connectivity.
Yes.
So it feels like conductance should increase, and then it makes sense. But here it's like you take one step in one graph, and then you take another step in the other graph, and both of these are once. I mean, basically, you have an edge if the U1 is connected to U2, and then V1 is also connected to V2. And that seems like you're just doing two walks in series.
Yeah.
And then it's like basically connectivity should be minimum of these two, so it shouldn't like it feels like it shouldn't grow.
It shouldn't grow. The connectivity will be minimum, but we'll actually prove it little more. This thing theorem will say. So I want to say, let's look at the eigen. So firstly, look at eigenvectors of what are eigenvectors that lives in R to the capital N. These eigenvectors live in J R to the capital small n, R to the small n. Therefore, the eigenvectors for G tensor H should be living in an n times n dimensional space. What's a candidate? This one I want to say, just take a vector there and take a vector here and take just like in the matrix you took element wise product, do the same thing for the vector also. So let's define. So if f is r times n and g is r times n, then let's define f tensor g in r times nn to be just f tensor g of some u comma v to be exactly f of u times g of v. Then it should not be hard to see that a of G tensor H. So suppose okay, more. A of G tensor H of apply that on the vector.
It's not U comma V, it's U into V.
Huh?
F tensor G, U into V is F of U times G of V.
U and V are the coordinates.
U and V are the coordinates.
Coordinates are indexed by
U
varying in capital N.
because it's an NN, this one, I'm indexing it with a pair of coordinates. One going in N, one going in from 1 to capital N, other going from 1 to small n.
But if the value is F of U.
Huh?
If you give the value F of U.
F of U into G of V.
No, so F cross G is also a vector.
F cross G is a vector,
So
but it has its indices. Where what's the vertex set for this? So the vertex set is capital N into small n. It's an n dimensional space. Therefore, the vertices are indexed by two. I can think of it being indexed by two guys. It's just, of course, this looks like a matrix, but I'm just flattening out the matrix and writing it as a single long vector. It is a tensor does look like an n by n matrix, but I am writing it down as a long vector of length nn. Okay. I want to claim this is true. Be a quick proof of this. So AG tensor H when you apply it on the F tensor G, and you're looking at the UVth element of this. This is what? This is summation over all U prime V prime AG tensor H U prime V prime UV. Sorry. It is UV comma U prime V prime of F tensor G of U prime V prime. This is just calculations. You just U prime V prime. This one we saw was exactly AG U prime. This was AH V prime. This is F U prime GV prime. So this splits into two products, AU, AGU, UU prime, FU prime into, this is U prime, this is V prime, AH, VV prime, GV prime. So what will this be? This is exactly AGF at the value U times AH AHG, the value V, which is exactly AGF tensor AHG at the value U comma. Yeah, so then what does this immediately tell you? If F lambda is what do you have? If AG F is equal to lambda F and AH G equals mu G, what do you get AG tensor H of? This is a candidate eigenvalue. What will this one be? Lambda mu times. So the eigenvectors are just going to be the all possible tensor products of all the eigenvectors. We have n eigenvectors, n capital n eigenvectors, small n eigenvectors, and you take all the n cross n, this ones, and the eigenvalues are going to be all possible products. And hence, the second eigenvalue will be the max because there is one and a whole bunch of guys smaller than it. So the first one has 1, lambda 2, lambda 3, lambda 4. The second one has 1, mu 2, mu 3, mu 4. Therefore, when you take cross product, 1 will still be the largest eigenvalue. And then the next one will be either lambda 2 or mu 2, depending on which one is the larger guy. Therefore, it will just be the eigenvalue of this one will just be the max of the two eigen. And that's exactly what you said. It cannot be any better than either of them. It will be the worst of the two of them. So more formally, I'm claiming is, where did we have this? This has eigenvalue, eigenvector pairs, Fi tensor Gj, lambda I mu j, or I and j. And hence we have the following claim. If G is ND lambda expander, stop writing it, and H is N D mu, then G tensor H. What's the number of vertices? That's easy, NN. What's its degree? DD. And what's its maximum of lambda? So now let's once again ask this process. Number of vertices, what's happening? The degree, what's happening? And the second eigenvalue and lambda. So this one is increasing. So that's a good sign for us. We are actually getting larger and larger graphs if we take tensor product. The degree is increasing, and this is a bad sign. I wanted to get larger graphs, but I wanted them with the same degree. I just don't want larger graphs with larger and larger degree. I want the same constant degree to be maintained as I go for larger and larger. Lambda was unchanged, which is a good thing. So these two are two operations. Both one lets you increase degree, other lets you increase lambda. But notice the degree is in both cases has been increased. So both these operations are going to increase degree, whereas what I wanted was an operation which will keep the degree constant. So what we are now going to ask, questions, what we're going to ask, is there a graph operation that reduces degree and not affect the other two parameters too much? And it was motivated by answering this question was when the zigzag. We will define a new product on graphs called the zigzag product, which will actually have this feature. It will decrease the degree without affecting the other two parameters together. Now we'll have these three operations. We'll have squaring, tensoring, and powering. We'll put them together to eventually keep build larger. So tensoring will make the graph larger. It will not be. So tensor will make the graph larger. That it will increase the number of vertices, but not necessarily it will not, but it will keep the eigenvalue unchanged, but the degree also increases. If you square this, the degree further increases. The number of vertices remain the same, but the eigenvalue decreases. Now, if you had this other operation, whatever is operation, if it decreases the degree without increasing the eigenvalue too much, then we could sort of trade squaring and zigzag product with each other so that, and then this will be the sort of operations we'll keep doing in order to keep getting a larger and larger. So the question is, what is this? What is this operation? There is a question. The motivation for this very clear. Why we want this? We have two operations, both of which work well with respect to the number of vertices and lambda. Each one of them does a good thing for one and doesn't affect the other one very much. But both of them, with respect to degree, behave badly. They are keeping on increasing the degree. So we want another operation which will sort of reduce the degree. There is undo the effect of powering and squaring with respect to degree. We want to undo it. So the most natural of such operation is what is called the replacement product. What is the replacement product? The replacement, so we want a process which will decrease the degree. So suppose you had a graph in which there was a high degree, this was a high degree vertex. Rather, we are always talking about regular graphs. Therefore, this is a vertex with, this is a U with degree D, and D is large. And we somehow want to reduce the degree. So now think of H is a graph on D vertices. So what we will do is we will actually we'll put a cloud at the vertex U. So H looks like this. H is some, this 1, 2, 3, 4, 5, 6. H is some graph on Is that 8 vertices? 5, 6, 7, 8, 9. The H could. H is something on 8 vertices. H is this one, graph. What we'll do is we'll think of this cloud and go and put this 8 vertex graph over here. That is, we'll think of H is say it's a graph, its vertices are I1, I2, I8 are its 8 vertices. We will think of a graph in which its vertex, the replacement products. So this is G. So G replacement H is going to have its vertices are going to be U comma I belonging to N cross D. So G is a ND graph. Forget about eigenvalues for now. And H is a, say, DD graph. It's a graph on D vertices with degree small d. Basically, what I'm trying to do is I'm taking every vertex of capital G, which has a high degree, and putting this cloud of vertices H on it. And sort of we are making, so it's, when you do this, when I combine this, it's going to look like, I'm going to put, let's put a H copy here. A copy of H is sitting where that cloud was sitting. I'm not doing this correctly. And then the edges are going out. The original, these edges, the G edges are going out from each of these vertices instead to the outside world. So,
I don't really understand.
so what I'm going to do is, so basically let's actually do it. Let me do it over here. Here. So suppose there is, let's look at a graph with 5 vertices. I want to replace. So G is an N 5 some lambda graph, and H is a 5 2 from mu graph. The 5 2 mu is for a 5 cycle, for instance, is a okay, we turn it around. What we will do is we are going to put the 5 cycle over here in this block and replace this, remove this large degree, and the vertices are now going to be these guys. So there was this cloud previously, but one large degree vertex is getting replaced. Every large degree vertex is, instead of a large degree vertex, we're going to stamp H.
Replacing one vertex with 5 vertices essentially.
One vertex, yeah. Every vertex, that's why N is going to the GRH, the vertices are going to be U comma I. The original vertex set of G and the vertex set of D. And we're going to replace this. And what it's going to, and this particular copy is going to have the entire copy of H sitting here. So in particular, U comma I will be connected to U comma J if I is connected to J. If Ij was an edge here, the corresponding U comma I will be connected to, because there's a complete copy of H sitting here. But in addition to that, if gamma Ui was V, if the ith neighbor of U was, rather, let's call it rot G, if the ith neighbor of U was V and from its point of view it was J, we are going to put the edge Ui is going to get connected to Vj. We are going to add that edge.
That is going to be in the tiny graph.
No, that edge is going to go from this cloud to that cloud. Yeah, that's a cloud to cloud vertex. These are within the cloud vertex.
What do we do with vertices which don't have enough neighbors?
No. We are assuming all graphs are regular graphs.
What's
Yes, it's a regular graph. We're working only with regular graphs for this, so we're going to do it this way. This is called the replacement product because you're replacing every single vertex of one graph with a copy of the other. Copy of the other graph, and edges is for all u in G, you're going to have ui is connected to vj if ij is connected if I is connected to j, that's one set of vertices, one set of edges. Another one is if rot g of ui equals vj, then ui is also connected to vj. So there are two types of edges. There is the internal edges and then the one long cloud. There's the intercloud edges and the intra-cloud edges. Notice the degree of this guy will be exactly d plus 1. So it's going to be degree of the h degree plus this one extra outer edge that is going out. So that's going to be the replacement product. So replacement product was studied for a while. Replacement product, nice. It's very intuitive. But there are two types of edges in it: the intercloud edge, the intra-cloud edges, and the intercloud edges, and these have different weights depending on whether it's a G vertex. This is a G edge, that's a H edge. So the zigzag product tries to get away this and comes up with only one. It's going to be some other operation on a related thing. It's going to do this and get just one type of edges, which are going to be the zigzag edges. There are not going to be two types of edges called intra-cloud, intercloud. It will be a combination of these both, and it will call it a single thing. So it's a slightly different product, which makes it actually easier to analyze. Here there are two types of edges, so it's a bit bothersome. So what we'll come up with is another graph product, which has only one type of edges, and it will be very similar to this, and that's what we'll do. So zigzag will be easier to analyze. Is an alternate graph product. It's very much inspired by the replacement product. It's called the zigzag product. And that's going to be the main how we're going to construct stuff over here. Zigzag, once again, G will be an ND, say lambda for now, ND lambda graph. H, so once again, think of G as graph on large number of vertices, the degree is large, and then we want to reduce its degree. And H is a graph on capital D vertices, its degree is small d, and say its eigenvalues.
The replacement product would also increases the vertices.
It increases the vertex much more mildly. It just multiplies it by a constant factor, capital D, unlike squaring or some such thing which it did. Unlike tensoring.
The degree goes down.
The degree goes down.
Like d plus 1 or something. And the eigenvalue would be the whatever.
We have to analyze it. So the whole point of this one is we won't be analyzing replacement products eigenvalue. We'll analyze zigzag, which is easier to analyze. That's the.
But I'm again trying to use this conductance sort of.
No, but once again, you have to now talk about the weights you're going to put on the intra edges and the intra edges, because they are not the same type of edges. And this weight is going to completely, this usual notion of conductance depends on how much weight you're putting on intercloud edges versus intra-cloud edges. That is, you need to decide that for replacement product, and hence it's not just the two edges are not treated equally, and hence it's not easy to analyze it.
They're not treated.
They should not be treated. One is an edge from there, one is an edge from here. You should give it, they are different types of edges, so you should give it different. So in order to get around this is where the zigzag comes in. So zigzag, let's talk about zigzag. So there is, once again, so there is the U cloud, and then there's the V cloud. So this is the U cloud, the V cloud. So U and V are two vertices of VG, and U is connected to V in G. Think of it that way. So now for both of them, we are going to do the same thing. We are going to put, instead of U, we are going to think as copy of H over here, a copy of H over here. So let's put a copy of H. And let's think of H as a slightly more complicated graph. Actually, that's ignore it for now. Let's just think of, that's a copy of H I'm putting to graph. I haven't yet told you what are the edges. So the zigzag product is going to be defined this way. G zigzag H. Its vertices are exactly the same as the vertices of the replacement product. Its vertices are n cross D. So every cloud and every vertex in a cloud is going to get it. So there is a copy of H. That's exactly the vertex set of this one. And notice there is this long, there is the G edge, which is now I have to talk about the edge structure of this. The edges are going to go from. So the way we'll do an edge is, let's take a particular vertex UI. Okay, let's call it. Call it U comma A. And I want to know when is a U comma A going to be connected to a V comma B. So think of U comma A is in N cross D. So firstly, before this, I want to say, I'm going to make this a D square regular graph. It's not going to be a D plus 1 regular graph, but a small d square regular graph. So in particular, I have to tell you this. If you give me, so I'm going to specify rot GZH of U comma A and a I comma J, where U belongs to N, A belongs to D, and IJ belongs to small d. So first thing we will do is we will compute B comma I prime, which is rot G, rot H of A comma I. So basically, we are going to ask what is the ith neighbor of A in H. So say that takes you this guy. That takes you to this. So this is from this point of view, it is the ith neighbor. And from here it is I prime neighbor. I should have put an I prime over here. Done. Is that okay? So the ith neighbor of A is B, and its neighbor is I prime. Then we just apply rot G U. You are in the cloud U. You just take the step B that is getting out of it. So this guy is labeled with B. And he's going to go to a B prime V. So rot G of B prime Let's assume it is V comma B prime. Let's move to that vertex. So this first step, you have taken such a step here, and then you have taken such a step. Now 3, you ask rot H of, you have gone to B prime and J. You ask what's the jth neighbor of this. That will be some A prime and J prime. So that is what this is. This is the vertex. This is the cloud V comma B prime. I'm going to V comma A prime. Should have done myself doing it. Okay, fine. Let me change. I'm not going to change things. V comma A prime, and this is J from this point of view, and J prime from that point of view. So it's actually, that's the zigzag. It looks like a Z. And the neighbor, and you're going to output V, the other cloud you went to, the neighbor you went to A prime. So that's the vertex you finally land up with. So if you start off with this, if this was your starting point, that's going to be your ending point. So for every such zigzag, you put one edge, green edge. The green edges are the edges in the graph. And so VA prime is the neighbor of UA, and what? And you went by the steps I comma j. To retrace it, you'll have to output the steps j prime comma I prime. Is that okay? So if you take j prime, you'll come to this. Then you go this way, you come back here. That's the thing. It's a zigzag step. It's this one. Let me just take this one off. Is the thing clear? So every step in the zigzag product is actually first an intra-cloud step. Then the intra-cloud step is told by which intra-cloud step is told by this first. So it's a d square regular. So I have to give you two indices I and j. Which intra-cloud step is given by I? So you go to another vertex in the cloud. Now the next one is a fixed step. There is no randomness in it. There's nothing from the thing. If you're at UB, you're here at UB, you take the B step out of U. You take the B neighbor, go out here. So you're now at the VB prime. And then you take a jth step. That's the entire. The zigzag is sort of a single step has both the step in G and two steps in H. Ideally, it should have just one step in H, but you want the graph to be an undirected graph. So if you started off with a H step, you have to end with a H step also. The last one is in order to make the graph undirected.
Only this green line remains.
The green line is the only thing that remains. The zigzag product, the edges are the green lines. But how do you get the green line? By taking a zig step or a zag step, and you have to take a zig step again, because in order to make the graph undirected. Otherwise, the edges have only a direction. So you make it zigzag. So that's the thing. And the graph is only the green edges. The zigzag product has the green edges. So notice that question. So GZH is a ND. The number of vertices is N capital D. Its degree is D square. And this is something we will compute shortly. And okay, I have explained it this way. Another way to explain it is the same thing which we just now saw. Take a particular edge, UV edge. There's a UV edge in the original graph, U and V. Now think of putting the whole H, the H graph over here. What is the zigzag product doing? For every UV edge, it's going to build a matching between, it's going to build a D square, a matching between the vertices here and the vertices here, a D square matching. And that matching is what are all the new edges in the graph. So it's going to look at all the D square B neighbors of this, all the D neighbors of this, builds a matching between them, and that matching edges are the edges of the zigzag. So the green, the zigzag expander, the zigzag edges are a matching between. So this was in our graph, this was, what was it? This was U comma A, U comma B, and B comma B prime. Are matching between the neighbors of B in the U cloud and B prime in the V cloud. We take that, the one edge is getting replaced by all of these guys. Okay, that's the zigzag graph. The one edge is going to get replaced by how many? This one, it's going to get exactly replaced with little d edges. Is that right?
All the neighbors of all the neighbors of B will be connected to
all the neighbors of this one. So little d edge, it will be the one neighbor is getting connected to little d guys over here. Little d should be d square, no? That should be d square. Why is it d? Second, it is. Yeah.
So is there only a particular edge UV between the two clouds?
Meaning? So there is, we stamping a copy of H for every cloud. For every cloud, we are going to stamp a copy of H. So originally G had N capital N vertices. Now the new thing has N times capital D vertices.
No, sir. Sorry, one thing not clear. So there's UB, BB prime.
Yeah.
For any B in the U, this B prime is fixed.
Yes.
So that's the matching.
Which one?
So the U comma I for all I, and then B comma J for all J, this has a matching.
Yes.
And then now you can look at every U comma, and then you'll have D square thing, right? Because I mean this thing has to be fixed first, right? Some other
U comma V comma B prime has to get fixed. That corresponds to
that's
one.
the matching. That's D. Thing.
That's capital D. So N into capital D. N into cap. So you have to fix a U or to fix a B.
I think complete bipartite.
It's a complete bipartite. It's a
Not a matching. It's a complete bipartite.
it's an involution. So it's a matching between N cross D to N cross D. It's a match.
Between the clouds.
Between the clouds, it's a.
Between the U comma B has.
U comma B has.
The neighborhood inside.
Yeah.
The cloud. That's a set of size D.
So yeah.
Neighborhood inside the right cloud. That's a set of
Size D. Yes.
The graph between them is not. Is this a matching or is this a complete? It's everything is going to be connected.
Actually, you have to.
So I can pick.
Yeah. So sorry. It's a complete graph between. This is true. This is zigzag edges is a complete. Yeah, that was wrong over here. The green edges take all the neighbors of U comma B and all the neighbors of VB and put the complete bipartite graph between these two. To see the picture. Yeah, sorry. That should have been what I said. So that's. So put it. These are these neighbors. These are these neighbors. You go and put. You look at the neighbors over here, and you put the complete bipartite graph between those two. So you put KDT. So the edges in GZH is a complete bipartite graph. Sorry. Between the neighbors of B in the U cloud and B prime in the V cloud. Yeah, so that's why you have the D square. A particular edge here is becoming D square. Particular edge in the original graph is going to become small D square edges in the new graph. Okay. Now suppose H was actually the complete graph. Suppose H was the complete graph. Then what would this be? The complete graph would say self loops.
So then this operation is just you take G, replace every vertex of G by two clouds, and then put all possible edges.
Yes.
That's exactly
the thing. So suppose H was a complete graph with self loops also put in. Then this is just replacing every vertex with a cloud vertices and putting a complete matching between them. The degree is what will be the degree of this graph? It will be capital D square, which is right because it's a complete. The H is actually a degree capital D graph. Therefore, the GZH will have the square of the degree of H, and the H degree is capital D here. Okay. And this graph should exactly be G. It is just a copy of G hanging around this one. This graph is got if you look at H with some other H, if you just look at G, this is just a copy of G sitting around. So what we want to now analyze, is I want to understand the following lemma. G is ND lambda expander. H is DD mu expander. I want to say GZH is certainly it's ND, that's clear. D square, it's clear. I want to put a number over here. And what is the number I put here? What will show, this has spectral gap 1 minus lambda. This has spectral gap 1 minus mu. Strangely enough, so you're taking 2 copies of H, 1 copy of G. And what we'll show is this happens to be the case. The spectral gap of this will be 1 minus lambda. That's 1 copy G, 2 copies of H, 1 expander graph. We'll show this in 5 minutes right now. And that's the way to remember this. There's a spectral gap here, there's a spectral gap here. this speckle gap, there are two copies of H sitting here, two steps. Every edge is two copies of H. Therefore, there's a speckle gap is sort of doubling. The speckle gap, this one. So notice this tells you that as long as this is any one of them is bounded away from one, this one is also bounded away from one. Is that true? No. If both of them are bounded away from one, then it is bounded away from one. And that should be clear. If one of them is disconnected, then the GZ will also be disconnected. If you draw this graph. Okay. Let's see a quick proof of this. So recall from last time, we saw this. Well, from last time, we saw that lambda of a random walk divided this way. We said W, a random walk, has lambda W less than or equal to lambda if W can be written as 1 minus lambda times W independent plus lambda times W error, where W independent is independent steps on steps of stationary. Rather, let me just write it as it is J times pi. And WE is any matrix such that norm of WE was less than or equal to 1. That is, it can be written as the perfect thing plus an error term. You could always write it this. Last time I had incorporated lambda into WE, but let's keep it this way. Okay. By the way, it should be clear that this is an if and only if. If I can write the graph like this, then its second eigenvalue is at most lambda. That should be obvious. So what we will try to write, GZH in some such way and try to understand how it behaves. Okay. So because of this, let's first understand GZH, the random walk. How can I write? The random walk matrix for this. I want to claim first, it's a random walk matrix for H times rot G times WH. This is exactly how this is a random walk matrix for GZH. Because, sorry, not this. I should be a little more careful. So this is a random, I want to write the random walk matrix for this. This is on N cross D. Now let WH be the random walk matrix of H on cross D. So IG cross WH is just on each copy of H, you're just doing the random walk of H, and I you are maintaining. So this is just this is like taking a step on H without altering which cloud you are in. So I want to claim once. What did I do? So there are 3 steps in the graph. There are 3 steps in the random walk. The first step is actually I tensor WH. You take a step within a cloud. That's exactly what that step is. The next step is just applying the matrix rot G. And the next step is once again I tensor WH. So I claim the random walk for GZH is exactly this operation. Are people with me on this? That's exactly how. Because first step is just a walk in the cloud. This is I'm dropping the subscript G. This is IG. You're not changing G at all. Then, based on it, you're doing a rod step. You're moving across, then doing IG tensor. It's a very concise way of writing the whole thing that we had written previously. Now, WH can be written as 1 minus mu times WH independent plus mu times some WH error. This is because WH has 1. So let's just plug that into this. IG tensor 1 minus mu. I'm going to drop the H. The same thing all over again. What does this look like? This looks like IG. This looks like 1 minus mu square IG cross W int rot G IG cross W int. That will just come out as this. And then there will be a whole bunch of other terms. Each of them is bounded with this one. All I want to claim, this is just 1 minus mu square, something into some matrix, which is say VE, where norm of VE is at most 1. You can check it out by whatever we said before.
How does norm behave under tensor product?
It will be the product of, because if we know tensor product, how it behaves with respect to, it will be the product of the norms. Therefore, it will very neatly just turn out to be this for some. So this doesn't affect my thing. It's that guy which is doing. That is not the independent one. You have to understand how, okay. Okay. What is W independent for H? It's just a uniform distribution. This is just 1 minus mu square IG cross JH rot G IG cross JH. Possibly I'll have to scale by a factor what do I need to scale by? I need to scale by, what am I doing? I need to scale by D square. It is all ones, I have to make it as this one, plus an error term. Now, what's this matrix look like? Now, H, this is exactly if I put the complete graph, what does it look like? This is exactly, forget about now, we have H is now the complete graph. If I put instead of H, I zigzagged it with the complete graph. What was the thing that I had got? It's exactly copies of G. So what I'm going to claim now, I want to do one step. So let's take, so I want to claim, let's take, so I want to take an F that lies in R and D and see how WGZH behaves on F. This is the same as how 1 minus mu square IG tensor G. And let's also take that F is such that F is orthogonal to the which one?
The top of the, it's 1 minus 2, B, the term, the constant term with B,
Yeah.
it should be 1 minus mu.
No, it's 1 minus 1 minus mu whole square, no?
Yeah, so the
Which one?
first term is 1 minus 1 minus 1.
So because it's going to collect a 1 minus mu from this WN and a 1 minus mu from the other WN.
Yeah, but I'm saying that that should be then 1 minus mu whole square.
Oh yeah. This one, the square is, this is sitting outside. You're right. Yeah. What I have over here. What I have over here. F is orthogonal to the all ones vector, and I want to know how F's length changes in the process. So let's look at.
Usually it's like this, whatever is happening, IG tensor J. So whatever that graph is, it's at least vertex expansion shouldn't be less than the vertex expansion of G.
Yes.
Because having, it's like the more copies you have, it's only better. You're sending out.
Yeah. So that's basically what I want to say. Take F when you apply. So right now we have thrown out H completely. H has gone off the picture. H is gone. Once we have mu, so it's now like G. So this can at most, this will shrink by a factor lambda because of this one, and that's it. So it will shrink by a factor lambda into 1 minus mu square. Here. Yeah, so what Mrinal is stating, let's see if I'll state it now, we might possibly revisit it next time. So GZH, which I want to say F. This is basically 1 minus mu square d square IG tensor JH dot G IG tensor JH applied on F plus 1 minus 1 minus mu square BE applied on F. So what's the want to make this following claim. This is what Ranal just now said, but we'll make the claim, and if we don't follow it, we'll go over the proof pretty carefully next time. Want to claim this looks like the first one is just this one is at most lambda times 1 minus mu whole square, size of this. That's how G will have to behave on it. Plus this is just because this will at most expanded by F, so this is just this term. So this is how this whole thing will behave, which is how much, which is This is a claim. This is 1 minus lambda 1 minus mu square size of f. What right? What I have here? Huh?
Yes, yeah.
Yeah, and that's this. This is basically the proof of this is exactly what Ronald said, but we'll stop now. We'll finish this proof next time. And that basically gives you the second eigenvalue. So just to go back, let's go back. That's a statement I had put over here. So this tells you that this one increases the degree drops. The degree from capital D is dropping to small d square. So small d square is smaller than capital D. You've got a degree reduction. The eigenvalues have not changed so much. If they were two constants before, it's become another constant. So now we are going to sort of we have these three operations: tensoring, squaring, and a zigzag. In fact, right now you can just take zigzag and tensoring, zigzag and squaring alone. You square a graph, its degree increases, the spectral gap decreases. Then you do zigzag, that you bring back the degree, but then the spectral gap is going to slightly worsen, but because you are considerably improved it by squaring it, this worsening is fine. So you'll alternate between squaring and zigzag and keep building larger and larger families of graphs. So just squaring and zigzag will give you a large family of graphs. The thing that you'll notice is this will not give you an explicit family. This will give you only weakly explicit. We will then bring in squaring, tensoring, and zigzag, all three of them together to get strongly explicit.
What is roughly the timeline of these things? Like building big expanders from small is it's already there. This idea is already there in the 80s with Bilu's work and right, these some version of these ideas were.
But Bilu's work is not that old, no? Firstly,
mid 80s.
No. Bilu's work is 90s or 2000. Jonathan Bilu, you're talking about, no? These lifts.
Yeah, the lifting.
I don't think it's that old. It's not that old. But this is very recent. This is recent in the sense this is 2005.
And the other, like the replacement product, etc.
A replacement product is older, but they never thought of using it to construct expanders. So I think this version of the claim, whatever claim we have here, such a claim was known for replacement products. They just didn't use this for constructing expanders.
What were they doing?
They were looking at random walks. That is, I have a random walk in which it's composed of one graph here and one graph there. I want to understand how well it mixes. So this was actually done by Dana Randall, Milena Mihail had these claims. The corresponding lemma for the replacement product was known. It was just not used to build expander graphs. So this happened only in 2005 or 2006. Or rather, the period between 2003 to 2007 is the conference versus the journal version of this graph. That's when this was constructed.
So this is the Wigderson.
This is this is RVW, Reingold, Omer Reingold, Salil Vadan, and Avi Wigderson. Yeah, and immediately after this, Omer used the zigzag construction to prove that SL is in L. Basically, he gave a log space algorithm. Some of you might be doing space in your complexity course. He gave a log space algorithm to traverse an undirected graph. The usual way of traversing an undirected graph is finds a non-deterministic log space if it's a directed graph. Now, if it's undirected, we didn't know of any better thing. We knew it was a randomized log space, but we did not know if it's deterministic. Immediately after RVW came Reingold's work, in which he showed a deterministic log space algorithm for traversing a undirected graph. That was an immediate consequence of this. But these all happened in 2003 to 2007. All of this. It's surprising that it was never looked at before. But LPS itself, LPS is mid-80s. LPS is mid-80s. LPS is mid-80s. That's a very different type of construction. This is a very computer science-ish construction. I'll go over the proof of this again. So I was hoping to finish this module completely. So this will get overflowed to the next Thursday, coming Thursday, in which we'll do half the lecture, we'll finish the proof, and then we'll get on to the other topic, which is multiplicative weight.